Of course, the purpose of this video is actually because when I was teaching in the class in the morning, where I realized the Zoom did not capture the lecture the way I wanted. So that is the reason why I'm actually making this video recording based on the permutation test that we did in the morning. Okay, so just like the way this was handled in the morning, I'm welcoming you to permutation tests, and of course in the outline, basically going to have a quick review, okay, on the bootstrap that we've done before, and of course also to react to the feedback that I got from students. Then after doing justice to that, I'm actually going to welcome you to permutation tests that we also call randomization tests, for one sample and two samples. Okay, so our four of us, start with a quick review, just like the way I did it the morning in class. I want to use this opportunity to appreciate students who actually provided our feedback. The feedback actually work a lot. Okay, a student asked a question that has to do with when is it appropriate or to consider, bootstrap T confidence and the bootstrap percentile confidence interval. Of course, I'm actually going to address that. And I'm also going to talk about, the bootstrap that we did before now. Okay, so the facts actually remain that we find ourselves in a world where we basically, want to take a decision that we don't want to regret. And at times we're looking for information, right? And of course, the information may be, one of the parameters. Of course, I told you parameter is a population characteristic value that we seek to determine. Parameter may be mean, it may be proportion. It may basically mean the difference of means or the difference of proportions, or at times it could even be ratio. Okay, so because we are actually seeking together, that become a parameter. And of course, the facts remain that if we really want to, get this, we're basically going to go into population. Now go into population. We don't have resources to capture everybody in the population because we're limited by budget. And most of the time, what we're going to do is to conduct survey where we're basically going to take sample. Now, taking sample, of course, it means we're basically going to estimate, the parameter that we're looking for in the first place. And of course, if I go into population, take a look at what I have now. Because we don't want to study the entire element in the population because we don't have resources for that. Okay. And we can't get the exact value of parameter. And another way is to go by way of sampling distribution. Because if we are working on the same thing, for instance, if I actually if you're interested in determining the average household income in the United States, and I decide I want to go into the United States population to choose a sample, if I choose 1,000 Americans and I ask them question, I figure out the sample mean. If you do the same, we actually, even though you are also choosing the same sample size that I choose, we're not going to get the same results. So if 1,000 investigators should go into United States population and take a sample, even if the sample is the same, don't forget, the SRS here actually mean we're using a simple random sampling approach, right? Because we're giving equal chance to everybody in the population. We're actually going to have several means. And of course, the means that we have become what I call a random variable. And as a result of that, we're actually seeking the probability distribution for these kinds of means that we're actually going to call that a sampling distribution of this statistic, because each of these is statistical. And of course, the sampling distribution of that is expected to follow normal distribution, okay? But you know what? We don't have resources to go into population several times. We don't have the resources for repeated experiments. Because if we do that, that has already defeated the idea of taking sample in the first place. And what we basically are going to do, we are guided by central limit theorem. And the central limit theorem actually puts it that when the sample size is large, and how large is that the sample that we're actually going to take, if it is at least story, okay, then we actually expect the probability distribution of these statistic values to follow normal, as you can see here. Okay, now which means we can basically use the normal theory. Every statistical model, has assumptions, and a model is as good as assumption put into a model. So, which means, so what we have assumption that actually validate, the idea behind statistical inference. So the idea behind statistical inference, before we can use statistical inference, the foundation of statistical inference is sampling distribution, which is what I'm displaying now. Okay, so what if in a situation where the population we're choosing from, like if you take a look at this, the population may be normal or not. If the population is not normal, provided that we're actually choosing a large sample, of course, we expect the sampling distribution, okay, of that, of the statistic to be normal. And of course, that would be center. The center of the sampling distribution here is basically going to be the value of a parameter, which is the population mean. Of course, that is why in statistics, we normally write the expected value, okay, of the X bar, okay, to be equal to the mu. Take a look at that. So what we're trying to say is that the mean, the average of the statistic should be the value of a parameter, which is exactly what this guy is showing here. Okay, so what if in a situation where the sample is normal? I mean, where the population is normal, the population you are choosing from. If the population we're choosing from is normal, we don't have issue about what the sample size is. Even if you choose the sample size less than 30, we actually expect the the probability distribution of statistic to be normal, because the population you are choosing a sample from is actually normal. Okay, that's exactly what I'm trying to show here. Now, what if in a situation, okay, where you have a small sample size, or you are choosing, the assumptions of normality is no longer holding, the population is not normal, the population is kind of skewed, okay? And of course, when you choose a sample, as you can see, what is being displayed here, this is more or less skewed, right? This is not normal. And of course, if I basically want to construct a confidence interval, then it means I'm using approach Okay, using approach that assume normality is going to be out of play. It's going to be out of place. It's not going to be appropriate. So if I want to construct a confidence interval now, so I'm actually going to use the idea of bootstrapping. And of course, I told you the other time, I have a original sample size. And of course, I'm actually going to produce a several versions of this. And that is actually going to give us this. There's several versions of that. I'm not going into population anymore. There's no new information. And the only thing we're actually doing, we are, in a way, producing several versions of that original sample, using sampling with replacement. So which means what you're actually going to see in each of this, bootstrap sample is, you're basically going to see repetition. You're going to see where some values in the original here, they are repeating. Okay, like I said, there's no new information. Now, based on the resample, you're basically going to compute the statistic mean, which means you are still using the conventional formula for each of that. And by the time you do the sampling, or you put into consideration the probability, the distribution of that, it should be normal. And what we actually have here is not a sampling distribution, but a bootstrap distribution. So the bootstrap distribution actually going to centered on the statistic value of the original sample. And why the sampling distribution that I talk about was centered on the value of the parameter. So because of that, I'm actually going to say, the center of the sampling distribution is actually going to be different from the center of a bootstrap distribution. Okay, I wanted to take note of that. Okay, so in a situation where you are now using bootstrap now, when you're bootstrapping a confidence interval, of course, you could actually use a bootstrap T confidence interval. You could use bootstrap percentile confidence interval, or you could actually use, the one where we're actually correcting the bias and the skewness. Okay, so what I'm actually going to tell you now is that in a situation where you get the bootstrap distribution, and then you use the histogram and you realize that for the normal distribution, of course, you're actually going to use bootstrap T confidence. Okay, you're actually going to use bootstrap T confidence interval. But when the probability distribution, I mean the bootstrap distribution, is not normal, then we cannot trust the bootstrap T confidence. Then what are we now going to use? Then we're basically going to use the bootstrap percentile confidence, depending on whether the bias is small. And what do I mean? Okay, by the bias. Okay, just like what I said in class, we actually get two types of bias. Okay, we have the bias that has to do with the sampling distribution, and we have the bias that actually that has to do with the bootstrap distribution. Let me tell you this: when you are talking about the bias that has to do with the sampling distribution, it means, if I go back right here now, okay, the bias that has to do with the sampling distribution is just trying to say, okay, the mean of all this has to be centered on mu, on the population parameter. The moment it is not, then we have a bias. So what I'm trying to say is that our situation where the expected value of X bar is not the same as this, then we call that bias. That's what we call bias. Okay, now we also have another bias that has to do with the bootstrap distribution, which I'm actually going to explain now. So when you talk about the bootstrap estimate of bias, What we actually mean is, that's going to be the difference, between the mean of the bootstrap distribution and the value of the statistic in the original sample. Now, what am I trying to say? In this original sample, okay, you actually have mean, okay. Now here, when you produce several versions of samples that are called bootstrap samples from original samples, you also compute, bootstrap mean, right? Now, the mean of the means here, okay, maybe basically I'm actually going to say S bar star, okay. Now, what I'm trying to say in essence about the bootstrap, the bootstrap sample, that means the bootstrap estimate of bias is that we expect, the mean of that, the mean of this, or to be equal to the, the mean of the original sample in the original sample. So which means we actually expect the mean of the bootstrap statistic, okay, to be equal to the X bar. Okay, so in that situation where it is not, then we are talking about the bootstrap estimate of bias. And don't forget, I said it the other time, okay, when we're talking about sampling distribution, the sampling distribution centered, it is centered on the value of the parameter, while the bootstrap distribution centered, okay, on the mean of the original sample. I want you to take note of that. Okay, even though the two distributions centered on different value of where, of course, the bias is similar. Okay, so I think that actually end the quick review on the bootstrap that we've done. Now we basically want to go into the randomization test. Of course, I told you the other time that if we actually want to talk, seeking redress, okay, if we want to, talk about, conducting statistical inference. Statistical inference is about testing hypotheses or constructing confidence interval. And of course, what we did before now, of course, if you look at the assignment, the ongoing assignment, that's actually centered on when the assumptions of normality does not fail. I'm actually talking about, the sampling theory hold. And of course, in their ongoing assignment, of course, I give you, question on hypothesis testing and on confidence interval. And of course, this actually centered, on the idea or on the assumption that statistical theory, the normal theory actually hold. And of course, when the normal theory fail, and I basically want to construct the confidence interval. Of course, I'm going to bootstrap the confidence interval. What if I want to test hypothesis? Okay, if I want to test hypothesis and the normal theory does not hold, of course, another alternative that we can actually use is what we call randomization test. We call it randomization test, and we also call it permutation test. And of course, the idea, is to perform a statistical test, and I would basically want to compute the p-value without any assumption about data. Of course, if you look at what we've done before, under the parametric, of course, we basically have assumption. Assumption was on, about the distribution of the data. But right now, so in randomization or permutation test, okay, we rely assumption on that. Okay, and of course, I just said now, a permutation test is the same thing as randomization test. Okay, the two names can actually be used interchangeably. Okay, so this is more appropriate, of course, when the normal theory assumption fail, most especially for small sample size. Okay, so if I want to conduct a permutation test, you remember the other time when we were conducting hypotheses using the parametric framework, Of course, we're actually using the idea of a normal distribution for the test statistic. Whether we want to actually conduct a one sample test or two sample tests, whether the focus is going to be on parameter mu or proportion or difference of means or difference or proportion. Of course, we actually base that, on the idea that the statistical theory, on the idea that the normal theory hold. And of course, if the normal theory fails, we're going to find ourselves using randomization tests. And of course, we have two approaches. Okay, when we want to use a permutation test or a randomization test. Okay, we call that the combinatoric approach. That's what we're going to do first. And that will be followed by a resampling approach. I want you to take note of that. And what do I mean by the combinatorial? Like in statistics, I don't know. Some of you have heard about combination and permutation. Of course, when I'm talking about combination, looking at the possible numbers of ways of selecting, object from, a whole object. You get what I mean? So here, we basically want to count the numbers of different arrangements of the data. Okay, and we're actually going to compute how likely the observed arrangements, okay, or more extreme occur. We should basically going to call that an exact test. Okay, and like I said, that is only visible for small samples because when you have a medium or very large sample, when you computing combination, that will be cumbersome. Okay, that will be so tedious. Okay, so of course, like I said, when you decide using the combination to know the possible number of different arrangements, of course, the next thing you're basically going to do is to, apply the idea of resampling or simulation. And of course, it means, just like the way we bootstrap the other time, we're actually going to, take randomly original sample from the population, and we're actually going to resample from the original sample, providing different versions of that. Okay, so that's what you see more than 5,000 times. And of course, we basically going to count the number of occurrences that equal or more, okay, more extreme than the observed statistic. Don't forget the observed statistic, the statistic that has to do with the original sample when the non-hypothesis is true, depending on what you are actually conducting hypothesis on. Okay? So, we can boost so many times with the aid of, high-speed computer that we have around. So because of that, the resampling is actually gaining popularity. So without computer, without high-speed computer, resampling, may be difficult to undertake. Okay, so the next step now. So how do we create randomization distribution? Now there's something I wanted to, put into consideration now. There's a difference between sampling distribution, bootstrap distribution, and randomization distribution. When I was talking about sampling distribution, that is the idea of, normal statistical theory, normal theory, okay? We're actually considering the possible samples that can be taken from population, but don't forget, we only go into population once, but, we're just talking about possibility. Now, in that situation, of course, we're going to be talking about sampling distribution. With a bootstrap distribution, don't forget the bootstrap distribution, we're actually talking about the probability distribution of several samples that we actually generate from the original sample. You know that? So we're going to be thinking, that is what we call, the distribution of, different, bootstrap samples now is what we call bootstrap distribution. So which means when we are talking about constructing a confidence interval using a bootstrap procedure, of course, we basically going to be talking about bootstrap distribution. But right now, we basically want to talk about testing hypothesis, and we're using randomization tests. Then we're actually going to be talking about randomization distribution. Okay, so so how do we now create a randomization distribution using resampling now? Of course, the idea, of course, in statistical analysis, if I want to take a decision regarding, whether to reject or to not to reject a particular hypothesis, of course, we basically need a p-value. But of course, when the normal theory hold, of course, the p-value we're actually going to generate is actually going to assume that the test statistic, follow normal distribution. But right now, our p-value is not going to be based on that in a randomization distribution. It's basically just going to be calculated, using the fact that the H naught is true, okay, then I'm also and after that, okay, then we basically we must actually generate randomization sample, okay, in a manner that is actually consistent with it not being true. Of course, don't forget, we're actually going to start using the original, using the data set from the original sample. There's something I wanted to know. It's not as if our models are failing us, but we are the one that we're not doing the right thing. Whenever we want to solve a problem, we need to be able to use an appropriate statistical methodology. And that was why I made an example in class when somebody commit an offense in Minnesota, and if that person is now being tried in a court in the state of California, even though if that court established the fact that that guy really committed the offense, whatever decision they take is basically going to be declared null and void. It's basically going to be an exercise in futility. Because the state of California does not have a territorial jurisdiction for the case. In fact, when the premise of an argument is false, so the conclusion. And that is the reason why we need to care about our, assumptions underlying the use of statistical model. Okay, so of course, this is what I said the other time. The randomization distribution is not centered at the same value as the bootstrap distribution. I told you. So the bootstrap distribution actually centered, on the value, the value of the value of the statistic in the original sample. Okay, but the randomization distribution is centered at the non-hypothesis being true. Don't forget, we use the randomization test that we also call permutation tests, to be able to test when the non-hypothesis is true or not. Okay, so that's going to be based on when the non-hypothesis is being true. I told you the other time, an accused person is actually going to be presumed innocent, okay, until he is proven guilty. And that is the reason why the non-hypothesis is basically going to be assumed to be true at the beginning. Okay, now, and I said the bootstrap distribution is centered at the observed value of the statistic. Okay, now, if you're working, for instance, I'm actually going to describe a scenario now where you basically, you're seeking to, investigate whether there's a difference between two means. Okay, you're focusing on the mean of sleep and the mean of caffeine group, okay, and you have 24 adults, and you basically want to partition 24 adults into two groups because we're working on two groups. You know that, right? Now, if I want to partition them into two groups, okay, and I basically want to use 12 here, and I also want to use 12. Okay, the possible numbers of ways. I'm talking about the numbers of unique arrangements now. The numbers of unique arrangement now is basically going to be 24 factorial divided by 12 factorial, then 12 factorial. And that is what is basically going to give you this guy, 2,704,156 unique arrangements. You know, the one I've demonstrated here is when we have, equal sample, like, yeah, the numbers of participants I have in each group is the same. I can also have situation or where they are not the same. Okay. So, for instance, if I actually want 14 in one group and 10 in the other group, of course, I'm still basically going to have 24 factorial divided by 14 factorial or 10 factorial. You get what I mean? That's what I'm going to have. Okay, but when you take a look at what I'm having now, so it's this guy. Now in this step 2, that's what I have. I have arrangement, right? Now in step 3, we basically want to count the number of arrangements where the difference between mean of sleep minus mean of caffeine group is going to be greater than plus or minus 3. So where do I get that 3 from? Okay, I got this 3 from the difference between this guy and this guy in the original sample. Maybe I collect the data, and of course, in the original sample, the difference is 3, right? Now, when that difference is 3, or what I'm just going to do, okay, is basically to consider these possible numbers of arrangement that I said here. So, which means the numbers of differences that I'm actually going to have is going to be that guy. And what I'm going to do now is to consider how many out of that are actually that have the difference greater than 3. And that is exactly what I'm going to do in number 4, where I'm actually going to divide. It's going to be the ratio of the number greater than the test statistic in the original sample when the null hypothesis is true, divided by the number of unique arrangements. When I do that, that will give me an exact p-value. Of course, that is going to be gold standard. The moment I have exact p-value, of course, automatically, I'm actually going to take decision, okay, regarding whether to reject the null hypothesis or not. You get what I mean? Okay, so to walk you through the process, basically going to show you the example of one sample, randomization distribution. Okay, just like what I did in class. Okay, the randomization distribution. Of course, I'm working with one sample. If I'm working with one sample, just like what we did in a parametric arrangement, where you actually want to conduct hypothesis about one population. Okay, of course, when the normal theory hold, you basically take a sample, right? We take a decision using the test statistic. We believe that the test statistic follow normal distribution, right? Okay, but right now we're actually going to start we're actually going to have an hypothesized value. Okay, I told you whenever there's a claim, investigation follows a claim, right? Okay, so we calculate the sample statistic from the original sample, okay, which is the mean, right? We also do the same in a normal statistical theory. And after that, we actually need to center the randomization distribution and the null hypothesis. So how am I going to do that? So it's just more or less telling me I should produce several versions of the original sample, and I'm actually going to compute the bootstrap the bootstrap statistic okay? And each of the bootstrap statistic now, okay, I'm actually going to be subtracting the hypothesized value. Okay, that's exactly what I'm going to do. Okay, now don't forget I'm doing that with sampling with replacement. Okay, and of course, I'm actually going to have my first randomization statistic, but I'm going to have several versions or several form of that. Okay, now for you, and of course, in the I'm actually going to repeat that like 5,000 times. Of course, you know that, right? Then uh, I'm actually going to locate the original statistic on the randomization distribution. Then I'm basically going to find the p-value. Don't forget, the p-value is just going to be the proportion of the randomization statistic that is more extreme than the original statistic. Don't forget, in the original statistic, okay, the original statistic is just going to tell you the difference between the sample mean and the hypothesized value. And don't forget, when you produce several versions of the original sample, you're actually going to have a bootstrap sample, okay, bootstrap sample 1, bootstrap sample 2, okay, until you get to the bootstrap sample mean 5,000. And the moment you actually have that, then you're actually going to go back, performing that, where you're going to be subtracting the hypothesized value for each of that. Then it means you're actually going to have 5,000 of these too. Look at that. You're going to have, 5,000 of this guy here. Okay, this guy is going to go from 1 to 5,000. Don't forget, this is a test statistic in the original sample. And this is you're going to have 5,000 here. And what we basically want to figure out now, how many of the difference here, the value that you got here, that is actually greater or equal to the difference in the original test statistic. The p-value now is going to be the number of that divided by the possibility. Okay, that's exactly what we mean. Okay, I'm actually going to demonstrate that to you now using an example. Now, take a look at this example now. Okay, a restaurant chain is measuring the levels of arsenic in chicken from its supplies. And the question is whether there's evidence that the mean level of arsenic is greater than 80 ppb. So we are now testing, of course, what we have in the non-hypothesis HO and what you have in the alternative. Of course, in the non-hypothesis now, is basically, this is actually telling us, mu, okay, is equal to 80. And of course, the alternative is basically telling you mu is greater than 80. So take a look at that. Now, we actually want to make use of 6 chickens because of the fact that it's very expensive to test for arsenic. So we're using 6 chickens, and in each of the 6 chicken, what we did? We tried to, quantify the arsenic level. The first chicken has 68, the second one has 75, and so on like that. The last one has 134. So take a look at that. Okay. Now, when you take a look at the data set that I have here, okay, you're basically going to see this is small, and at the same time, this is more likely to be skewed because of this guy. Take a look at that. Okay. Now, testing out this hypothesis now, we're basically not going to use a normal theory because the assumptions of normal theory fails. So now the question now is, okay, what does the sample mean for the data? And find a p-value and give a conclusion for the test. Should the restaurant chain stop ordering chicken from that supplier? That depends on whether we reject the non-hypothesis or not. Okay, so how do we now do this? If I want to do this, if I want to conduct a one sample randomization test, and I basically want to use an R software, how am I going to do that? Don't forget the first question actually said you should find the sample mean. of the data. Of course, you want to get a sample mean of the data. You're just going to write the data now. Then you're going to do the mean arsenic. That will give you 91. That is sample mean of the original. Don't forget the mean of the original sample. And don't forget the hypothesized value of the mean is 80. Okay. And don't forget, we want to see whether there's a difference. The effect size now is basically, if I want to measure effect size, it's going to be the difference between the sample mean and the hypothesized value. Okay, so here now, I want to find a p-value and give a conclusion for the test, because the conclusion is whether the restaurants should stop ordering chicken from their supplier or not. Okay. And don't forget, which means we basically need to create a randomization distribution, and the randomization distribution should be consistent with the HO, okay, when the null hypothesis is true. Okay, don't forget, the randomization distribution is created by sampling with replacement, just like the same way we bootstrap. Okay, so number 3, we need to, four of us get the difference between the sample mean and the hypothesized. Don't forget, that is the sample mean, and this guy here is the the hypothesized value. So we get the test statistic, the original, the original test statistic is actually going to be based on that. Now, the next thing now, we actually that you see us doing here now, okay, we of course, we want to resample 5,000 times, which means on the original sample, we're actually going to produce several versions of that, which is like 5,000 of that. Okay, now when we produce 5,000 of that, it means we're basically going to have 5,000 bootstrap means. And of course, each bootstrap mean, I'm actually going to subtract hypothesized value of 80. So which means I'm basically going to have 5,000, differences. And all what I'm telling her to do now in the code that I'm being displayed is that, Arrow should figure out what is the numbers of times. Okay, when I look at the difference between the bootstrap mean and the hypothesized value, I really want to know the numbers of time is basically going to be greater than the difference between the original sample mean and the hypothesized value. That's exactly what I'm trying to do here. That is the adjusted dot arsenic, that. So in the end, and of course, I'm still, don't forget, this is like a bootstrap, the 5,000 times that I'm doing that, I'm actually going to have sample of 6. Don't forget, original sample that I have is 6. And of course, I'm actually going to have several versions of 6. Okay, that's exactly what you see. So when you follow this code that I'm actually displaying, of course, you can now determine your p-value. Okay, now don't forget, the initial statistic or the mean of the original sample is 91. Okay, so I of course, what I actually wrote now, so the mean, what is it, I'm actually considering the average, the random dot dst greater or equal to that, and of course I have the p-value to be 0.112, and of course when the p-value is 0.112, of course that is greater than any reasonable level of significance, and because of that, we're going to fail to reject the null hypothesis. Take a look at that. Okay, so this is another example. This example now is basically going to be on the one sample proportion. Scientists from the University of Arkansas have managed to train a dog into detecting the difference between urine sample belonging to patient with and without thyroid cancer. Okay, so we know dog do a lot of good job. I remember when I was going to present my PhD work at the University of Oxford in the United Kingdom in 2015, when I was actually given scholarship to do that from Nigeria. upon my arrival at the Heathrow airport in London, of course, we were actually welcome with dogs. Of course, upon the arrival of a visitor, the dog is actually, want to know, they're going to use a dog to detect some stuff, whether you carry some prohibited goods or something. Okay, so right here, a Frankie, a German Shepherd, was taught, to lie down if he detected sign of thyroid cancer, okay, in the urine sample. And if the test was negative, okay, the Frankie would turn away from the sample, of course. I remember then when the dog actually approached me, and in the end, the dog actually turned away. Okay, so Frankie was actually given 34 samples, and the Frankie was able to correctly identify story, okay, and the question now, does he really have the ability to detect thyroid cancer? Or maybe this guy is just this dog here is just using it's just guessing, okay, and because of that we basically want to conduct an hypothesis. Of course, what you're actually going to see in HO is the proportion is 0.5, because the 0.5, 50%, when you are guessing at random, where there's equal chance that the dog could detect that or not. Okay, and of course the alternative is basically going to say, oh, this dog is not just discovering that by chance. He knows what he's doing, with regard to detecting thyroid cancer. Okay, so if we really, this is the step now. Of course, we basically need to use the original sample to determine the p cap. Don't forget, in class, the p cap I said is x over n. N is the sample size, and x is the number of characteristics of interest. Of course, we've been given here that out of 30, the probability that this dog can actually detect something correctly is 30 divided by 34, which is 0.88. Okay, so that is basically um gonna be is 0.88235529. Take a look at that. Now we actually want to figure out a p-value and give a conclusion for the test, on whether the dog should be trained and used to detect certain type of cancer. And here we're also going to curate the randomization distribution that's actually consistent with the H naught. Okay, and that is basically going to be done by simulation. Now, like I said, we actually need a generator now, but we need to be visiting a probability distribution because of the fact that the nature of the random variable here is categorical. We got two possible the outcome is, we have two possible outcome here. We're basically going to be simulating from binomial distribution. Okay, now when you take a look at this guy, this is just the number of repetition. We basically want to allow 1 million now. Of course, we'll be using 5,000. We can use greater than that. Okay, so that's exactly what I'm actually going to say. So like, yeah, I'm trying. So take a look at that. So that is a repetition. And of course, I'm actually simulating, given that the H naught is true. And of course, the parameter there is basically going to be 0.5. If 0.5 is used, that's actually talking about 50-50 chance. So which means the dog doesn't know what it's doing. Okay. And so for I in 1 in n, okay, so since I'm actually using binomial distribution, the arrow code for that is basically going to be arrow binom. And of course, I'm basically going to write 1 comma, the sample size. okay, then it's 0.5, which is a hypothesized value. Okay, so what I basically want to do now is to find the p-value, which is basically going to be, I want to determine the proportion of sample greater than the original proportion that I have. Don't forget, the original proportion that I have is that. So when I do like 1 million, of that, okay, how many of that, the p carb that would be greater than the 0.8823, okay, and so of course it's very, very small, okay. So what I'm trying to talk about now is when I actually do that. So this is, putting into consideration here, okay, that we are still using the same formula of x divided by n. Don't forget our n is 34, because when you are getting each bootstrap proportion, you're still going to use x over n. Okay, so in the end, the p hat, the distribution, the value that is actually greater or equal than this guy. Of course, when you find the ratio at the end of the day, we got the p value of this, which is very, very small. Now the p value here is very, very small compared to the level of significance. We're basically going to reject the non-hypothesis and conclude that, of course, the dog can actually be used to detect thyroid cancer. So take a look at that. Okay, so this is the randomization distribution. Of course, this is where I'm actually going to start the next class, where I'm going to talk about two sample randomization tests. Okay, so until the next class, make sure you stay safe and have a very beautiful day. Bye for now, everyone.